In this activity, we'll be essentially reproducing what we did for first-order differential equations, now looking at second-order differential equations. And looking at this differential equation, so it's our generic second-order differential equation, and using a math and Laplace transform approach in order to look at the various ways to identify solutions. So we're going to verify that this solution type is indeed a solution, and then we're going to identify what values of R will make it a solution. So there's going to be some contingencies to make this a solution. And then we're going to take a look at using the Laplace transform, essentially take the Laplace transform of the differential equation, solve for y, and then use the inverse Laplace transform to identify the solution, and show how both of these give the same result. So go ahead and pause and work on this problem. So our first approach is to plug in the solution and show that it is indeed a solution. So here we're saying that y is equal to e to the rt, and so the second derivative of that is r squared e to the rt. And then we have a1 times the first derivative, brings down 1 power of r, e to the rt. And then we get a0 times, again, the value of y, which is e to the rt. And that should be equal to 0. So now we factor out this e to the rt, and so this should look a lot like what we did on the previous video where we talked about generic solutions, where we get r squared plus a1r plus a0 is equal to 0. And like what we said before, this exponential is never 0. It asymptotically approaches 0 as t goes off to infinity, maybe, if r is negative, but it is never 0. And so it's this term here that must be 0 in order to guarantee that this is a solution. So the contingency, the requirement, is that this polynomial is equal to 0, and that specifies what the values of r need to be in order for it to be a solution. So if r is this unknown, then we think about that as a quadratic, and so we solve that with the binomial formula. So that's simply the values of r that solve this, that are the roots of this polynomial, are minus a1 plus or minus the square root of a1 squared minus 4a0 all over 2, just over 2. So these two solutions, so you would plug in whatever a1 and a0 would be in your particular case, and that gives you the solutions r1 and r2 that form the overall solution. So that means that, yes, y is equal to e to the rt is a solution, but specifically the solution, the complete solution, looks like this, and it has two pieces, one for a solution where it's specified by r1, one where the exponent is specified by r2. And so r1 and r2 are given related to a1 and a0 like this. So now let's take a look at the Laplace approach. In the Laplace approach, we go ahead and take the Laplace transform of the differential equation, and we get this term for y double dot. We get this term for y dot, and notice that both terms get that a1 coefficient. You got to multiply that all the way through, and then you get y for the little y. And so if we solve for capital Y and put it in terms of the initial conditions, we get these two initial conditions up here. And that's not really the important thing. For us right now, the really important thing is this denominator. Because what this ends up being is when we separate this into our different partial fractions, we want to get two terms that look like s minus r1, s minus r2, where these are, again, r1 and r2 are just like what we had before, are the solution of this differential equation, or the two roots, sorry, the roots of this differential equation. And so, again, using binomial theorem kind of gets you there. And so it's this bottom that specifies what the shape or the functional form of the solution looks like. These C1 and C2s are certainly going to depend on these different coefficients and the initial conditions, but the actual form of the solution is determined by the denominator. And these are going to be, when we take the inverse Laplace transforms, these become these two exponential terms, and the two r's specify the two rates. So if you really wanted to go through it, in gray here I have the solution to the actual coefficients, but again, that's related to all these different parameters, but in principle, the functional form, this exponential piece, is not going to change. It's just the amount of them, which is given by C1 and C2. And what you'll note is you get the exact same solutions just like we did before, and we see it two different ways. And so this polynomial that we get in both approaches recurs, and the reason for that is because it is what specifies the heart of the dynamics of this differential equation. And so we're going to start to give these specific names as we go forward.